back to the original packet, page 40. For some reason, I don't know why I did this, but in case you forgot how to add matrices, well, it's possible, I guess, because we talk a lot about vectors and operations between matrices and vectors, but not necessarily a lot about matrix operations. So, you know, just in case you were wondering, and it all works the same way. If we look at a matrix as the accumulation of vectors in column form, then it's just basically two by one vectors compiled to give us matrix A, and then two by one vectors to give us matrix B. Right? And how we operate on those will tell us a bunch of things, and that's going to be kind of like where we're going to start our journey in, you know, explorations as we move forward. So really, it's just, you know, 1 plus 5. You're adding corresponding parts. 2 plus 7. I so very rarely have fill in the blank that I don't want to like waste this opportunity. So 3 plus 2. 4 plus 0. Right, but again, a lot of this stuff the calculator will handle, and we don't really very often, or we're not very often going to be bogged down with the arithmetic. So it's going to be a lot of calculator work just to kind of save us from a lot of this stuff. But you see, we just did it with 2 by 2 square matrices. We can do it by 2 by 3 matrices. We can do it by 10 by 10 square matrices. We could 2 by 3 matrices. As long as the dimensions are the same, addition is something that you can do. All right. The actual notation for a matrix, we're going to actually start moving towards that, just because we'll need that for something called cofactor expansion and you know, finding determinants and things like that. So when we write something like a sub 1, 1, it's not a sub 11, it's a sub 1, 1. So first row, first column. All right, so we have the ij notation, so the ith row and the jth column. All right, so the 1, 2, first row, second column. Right, but, you know, as long as you understand that, you know, the naming convention for these things, it becomes pretty easy. Right? That's going to be an organizational strategy that we'll use when deriving something called the determinant, because it involves permutations, which is one of those probability concepts that I told you I was terrified of when I first started teaching. Now I have a great understanding of it, and it's wonderful, and I see all the applications of it. It's outstanding. That doesn't mean you're necessarily going to like it, but it'll serve its purpose. Right? You're talking about different arrangements of things, and when you look at this, for example, this matrix over here, you see 1, 1, 1, 2, 1, 3, then 2, 1, 3, 1, and so on. It looks like the sample space for the rolling of 2 dice. Right? So if you were to limit it at 6 by 6 matrix, that's pretty much what you would have. Right? So you're looking at all the different arrangements of outcomes when you're rolling 2 dice. So there is something to this whole probability component. All right, so we'll tackle that as we go. Scalar multiplication we know, so just using the notation form. It looks slightly different, but that's what it would look like. I'm using the scalar R instead of the scalar K. So R capital A can be thought of as the same thing as R times lowercase a sub ij. Right? Lowercase represents the entries within the matrix with the same letter. Right? And when you sub it, you apply the appropriate subscripts. That identifies what particular component that you're looking at. All right. We have the transpose of a matrix. A to the, I guess, t power is the same as a to the t power of n by n matrix. right? So it's the reversal of the components, right? So I'll kind of illustrate that in a second. Basically, the shortcut way of thinking, I guess, is that you're just taking your columns and you're swapping them with your rows. So row 1 becomes column 1, row 2 becomes column 2, vice versa. Right? So the sum of A and B is very straightforward. You got 4, you got negative 4, you got 1, you got another 4, you got a 6, you got a 1. Twice A, scalar multiple of A, is 2, 6, 2, negative 8, 10, 0. Right, now when we're talking about the transpose of a matrix, right, so A, matrix A, is of a 2 by 3 variety. So the transpose is going to be 3 by 2. So your first row, 1, 3, 1, becomes your first column, 1, 3, 1. Your second row, negative 4, 5, 0, becomes your second column, negative 4, 5, 0. Right. Now, there is a really good justification for why you can do that under certain circumstances, but that is a different story for a different day. But it comes from this concept called duality, and we'll deal with that down the line. But basically, there are certain circumstances that allow us to change the orientation of a vector, right? So or change a matrix into a vector. All right, it has to do with symmetry, and it has to do with the distance that that the vector is away from a particular benchmark. So we'll cross that bridge when we get to it. But this is a powerful tool because it allows us to think of an orientation as, in some cases, interchangeable, which allows us to perform operations under certain circumstances where we might not otherwise be able to. All right, so that's something we haven't really delved into conditions behind matrix multiplication, but we're about to hit that, and you'll see that under certain circumstances you can't, and under other circumstances you can. All right, and when we get to inverses, you're going to see even more. All right, we talked about the dot product already, so just a little recap of that. I'm just pausing because I'm like, now that I gave you the supplementary packet, my little add-on, I'm not sure this needs to be here anymore. All right, yeah. So because I want to give typo bonus to as many people as possible. On page 41, we'll say, if somebody wants to submit this, say consider removing dot product definition. Because I haven't decided whether or not I want to remove it. Because it might be like a good recap, but it might not. It might be just completely superfluous. I'll consider it on my own time instead of staring at it blankly. All right, so we talked about multiplication of matrices, matrix against vector. We talked about little shortcuts here and there. The best shortcut, obviously, is the calculator. But if you needed a by hand shortcut, there's another way to go about doing it. But anyway, we have a matrix 1, 2, 3, 4. We want to multiply it by the column vector 5, 6. This is the way we kind of lived in the last unit. So we would take the 5 and multiply it by the 1 and the 2, and we would take the 6 and multiply it by the 3 and the 5, and just go from there. So what we can do here is apply a little bit of a shortcut. It's honestly can't remember if I showed you this shortcut. So if I did, sorry for doing it again, I guess. If I didn't, Here's a shortcut. So we have a 2 by 2 matrix being multiplied by a 2 by 3 matrix. So 2 by 2 multiplied by 2 by 3 should give us, as a result, a 2 by 3. Should, as in, if we do it right, it'll give us a 2 by 3. Right? Not as in, you know, it should, like, if math doesn't break, no, like if we don't break. All right, so 2 by 3 matrix, somehow. All right, some of you may know this shortcut. And again, this is really just a shortcut to breaking it up like we did in the last unit and writing a bunch of different matrix vector products just to clean it up. Basically what you're doing, and it's more of a visual thing, is you're picking up this row 1, 2 and multiplying it by the column 0, -1, right? Corresponding parts. Right, so just kind of off on the side or in your head. In your head is preferred, obviously, but it even took me a while to get a handle on this. You're taking the 1, multiplying it by the 0, the 2, multiplying it by the -1, and adding it together. All right. So, just to combine some thoughts here, what you're really doing is taking the dot product of the transpose of the rows of column of matrix A and the columns of matrix B, or matrix C in this case. Right? So, and we'll talk about notation and how to express this down the line. All right, so the transpose of this, so making row 1 become column 1, making row 2 become column 2, and just going doop, 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 and then row 2 become column 2, and then doop, doop, doop. Get each of those dot products, those become the entries. All right. Obviously, the calculator is less likely to screw this up, unless it's a user interface issue. But what most people are comfortable doing anyway is just saying, all right, I'm taking these two guys, multiplying it by the second column. What do I get if I take the first entry in the first row with the first entry in the second column? I get a 1. Second entry is giving me a 0. 1 plus 0, is 1. I almost said the wrong answer. One times 3 is 3. 2 times -2 is -4. 3 plus -4 is -1. And then just repeat the process. Zeros are helpful. 3 times 0 is 0. -1 times -1 is +1. The sums are 1. 3 plus 0 and then 9 plus 2. All right, so again, it's essentially the transpose. So I'll write it separately just so you get a sense. But it's like saying I'm taking 1, 2, dotting it with 0, -1. I'm trying to make fractions out of this for some reason. dotting it with 1, 0, 1, 2, almost made that a fraction 2, dotting it with 3, negative 2. Then doing the same thing with the bottoms. So 3, negative 1, 3, negative 1, 3, negative 1. So I have 0, negative 1, 1, 0, and 3, negative 2. So each of those dot products, so transpose of each of the two rows, multiplied by each of the columns. Or you can put in matrix A is matrix A in your calculator, matrix 2, matrix C, whatever. Multiply them, call it a day. All right, so think about under what circumstances a product would exist. The only way that that would happen would be, well, we would say that the number of rows in the second matrix would have to be equal to the number of columns in the first matrix. Number of columns equals the number of rows. But really, it's more basic than that. It's under what circumstances would you be able to find a dot product when you find the transpose of the rows in the first matrix? The only way that that would happen is if you were to turn each row on its side, making the transpose. As long as it had, each one of those rows has the same dimensions as each one of the columns of my second matrix, in order to allow me to find the dot product, then I'm good to go. If I can't find the dot product once I make that maneuver, then I'm out of luck. All right. So when we look at the second example, we ask ourselves, is that a possibility? Well, can I find the dot product between a 1 by 1 matrix and a 1 by 1 matrix? Well, yeah, sure. So it works out just fine. And besides, we know that we're on the lookout for a 3 by 2 matrix. Uh, 3 by 2. All right. So dot product of 1 and 4, dot product of 1 and 5. 2 and 4, 2 and 5, 3 and 4, 3 and 5. All right, so I'm going to put a star on the next example.